In mathematics, the Dedekind zeta function of an algebraic number field K, generally denoted zeta K, is a generalization of the Riemann zeta function, which is obtained by specializing to the case where K is the rational numbers Q. In particular, it can be defined as a Dirichlet series, it has an Euler product expansion, it satisfies a functional equation, it has an analytic continuation to a meromorphic function on the complex plane C with only a simple pole at s equals 1, and its values encode arithmetic data of K. The extended Riemann hypothesis states that if zeta K equals 0 and 0 less than Re less than 1, then Re equals 1/2. The Dedekind zeta function is named for Richard Dedekind, who introduced him in his supplement to Peter Gustav Lejeune Dirichlet's Volksungen über Zahlentheorie. Definition and basic properties. Let K be an algebraic number field. Its Dedekind zeta function is first defined for complex numbers S with real part Re greater than 1 by the Dirichlet series where I ranges through the non-zero ideals of the ring of integers OK of K and Nk. Q denotes the absolute norm of I. This sum converges absolutely for all complex numbers S with real part Re greater than 1. In the case K equals Q, this definition reduces to that of the Riemann zeta function. Euler product. The Dedekind zeta function of K has an Euler product which is a product over all the prime ideals P of OK. This is the expression in analytic terms of the uniqueness of prime factorization of the ideals I and OK. The fact that, for E greater than 1, zeta K is given by a product of non-zero numbers implies that it is non-zero in this region. Analytic continuation and functional equation. Erich Heck first proved that zeta K has an analytic continuation to the complex plane as a meromorphic function, having a simple pole only at s equals 1. The residue at that pole is given by the analytic class number formula and is made up of important arithmetic data involving invariance of the unit group and class group of K. The Dedekind zeta function satisfies a functional equation relating its values at s and 1 minus s. Specifically, let delta K denote discriminant of K, let R1 denote the number of real places of K, and let n where gamma is the gamma function. Then, the function satisfies the functional equation special values. Analogously to the Riemann zeta function, the values of the Dedekind zeta function at integers encode important arithmetic data of the field K. For example, the analytic class number formula relates the residue at s equals 1 to the class number h of K, the regulator R of K, the number W of roots of unity in K, the absolute discriminant of K, and the number of real and complex places of K. Another example is at s equals 0 where it has a 0 whose order R is equal to the rank of the unit group of OK and the leading term is given by combining the functional equation and the fact that gamma is infinite at all integers less than or equal to 0 yields that zeta K vanishes at all negative even integers. It even vanishes at all negative odd integers unless K is totally real. In the totally real case, Carl Ludwig Siegel showed that zeta K is a non-zero rational number at negative odd integers. Stephen Lichtenbaum conjectured specific values for these rational numbers in terms of the algebraic ktheory of K relations to other L functions. For the case in which K is an abelian extension of Q, its Dedekind zeta function can be written as a product of Dirichlet L functions. For example, when K is a quadratic field, this shows that the ratio is the L function L, where chi is a Jacobi symbol used as Dirichlet character. That the zeta function of a quadratic field is a product of the Riemann zeta function and a certain Dirichlet L function is an analytic formulation of the quadratic reciprocity law of Gauss. In general, if K is a Galois extension of Q with Galois group G, its Dedekind zeta function is the Artin L function of the regular representation of G and hence has a factorization in terms of Artin L functions of irreducible Artin representations of G. The relation with Artin L functions shows that if L K is a Galois extension then is holomorphic. For general extensions, the result would follow from the Artin conjecture for L functions. Additionally, zeta k is the Hauser-Weil zeta function of spec OK and the motivic L function of the motive coming from the cohomology of spec k. Arithmetically equivalent fields. Two fields are called arithmetically equivalent if they have the same Dedekind zeta function. Wiebe, Bosma and Barter-Smit used Gassman triples to give some examples of pairs of non-isomorphic fields that are arithmetically equivalent. In particular, some of these pairs have different class numbers, so the Dedekind zeta function of a number field does not determine its class number.